why do you use fixed volume? Because it works. This is what I tell my students, that sometimes you just need to like do it and think afterwards how to argue that this is the correct way. And of course, you should expect it to be this way because of this. And, but in reality, initially you just don't know. And right. Second of all, I think it's a very interesting way. Like if we try to formulate a new, more deep formula of quantum gravity, right? So we have this in this situation, we have some hints, right, of what can work and what cannot work. For example, one of them is black hole thermodynamics, and basically you're turning it around and say, okay, let's assume what things we need to assume that will lead us back to the quantum gravity. To general relativity. So my question, as you said, one of the main points will be if we can learn anything new, which apparently I think there's still not a definitive answer there. But maybe another question that you can clarify for me is the physical picture of what you are proposing now. Like instead of proposing Einstein questions, just the equation, and then we see that the consequences are correct, let's say. What you propose now is the black hole thermodynamics and this principle of maximal entanglement. So maybe, and this lead to general relativity. So maybe you can explain the physical frame for me. I'm sorry, I didn't get it, of this maximum entanglement entropy principle.
Right. I can't say almost anything really cogent about it, except that maximal entanglement seems to be a kind of equilibrium property to me. Like, because if complicated systems have settled down, they're interacting with each other. Like, for example, about the, what's it called? The eigenstate thermalization hypothesis, or maybe just eigenstate thermalization, because it's proved to some degree in quantum mechanics. You take a complicated quantum system, put it in an energy eigenstate, a random state, but just then carve out a subsystem of it and ask, what does the reduced density matrix look on that? If the system is a complicated enough system, it will be almost exactly describable by a thermal state in the subsystem. And that's one way of accounting in quantum statistical mechanics, in a way, for why are systems and subsystems in equilibrium well described by the canonical ensemble. So I guess I'm saying, and the canonical ensemble maximizes entropy at fixed energy. So somehow entropy maximization seems to be just a natural outcome of complicated things interacting with each other. Entanglement entropy maximization, because everything has had a chance to get entangled with everything else. So if I think of a big universe having in its old age, it's had plenty of time to settle down, whatever the microscopic fundamental description is, it's settled down into its state that is maximally entangled. One region is always maximally entangled with the adjacent region. If it weren't, it's like information would flow, something would still be happening. So this is completely hand waving, but it's the way I think about why would it be natural that the vacuum would have this maximal entanglement property. I mean, of course, ultimately, this would really only be satisfying if we could derive it from some fundamental underlying theory. So I'm not aiming that high at this point.
So in a sense, we can see it as some kind of zero law, where you say, like, if it weren't, there will be some transfer. Instead of heat, transfer of temperature will be a transfer of information to get the entanglement.
Mm-hmm.
Right? Okay, so
yeah,
very interesting idea. So I don't see any more questions, so I think this is the moment then to end by thanking our speaker. So if you can, please turn on your cameras and microphones so we can thank Ted. Thanks again, Ted, for your talk. So, con esto terminamos la escuela de verano, ¿verdad? Si no me equivoco. Aprovechando que Alberto Sánchez está aquí, ¿quieres